This is Rosen, Discrete Mathematics and its Application, Section 2.1. We are discussing sets and their properties. Here we are talking about set equality, and not surprisingly, we say that two sets are equal if and only if they have the same elements. And one of the ways we can write this is using propositional logic notation and the element symbol. So for every x is an element of A if and only if x is an element of B. And here we have two sets that appear different, but they are actually equal because they have the same elements. All right, subset. We say that A is a subset of B if and only if every element of A is also an element of B. And we use the notation with this open curved like a U on its side with a line under it to represent the subset relationship here of A to B. And we can represent that symbolically, that A is a subset of B if and only if for every A, X is an element of A implies X is an element of B. So there's a relationship between the concept of subsets and implication. Now note that since X is never an element of the empty set, that the left side, the hypothesis of this implication, is always true vacuously. Therefore, the empty set will be a subset of every set because that X is element of an A is always false. Also, because X is an element of S implies X is an element of S, then every set is a subset of itself. All right, so we'll use those definitions to show whether one set is a subset or not of another. And in order to do that, to show that A is a subset of B, we show that if X is an element of A, then X is an element of B. And to show that A is not a subset of B, we can find a counterexample, an X that is in A that is not in B. Computer science majors at your school is a subset of all the students at your school because every computer science major at our school is also a student at our school. On the other hand, here we have a set, two sets. Integers with squares less than 100 is not a subset of the non-negative integers. And one counterexample of that would be -1. -1 is not a non-negative integer, but its square is a square less than 100, is a number less than 100. Okay, so remember A is equal to B as sets if and only if this is true, X element of A, if and only if X is an element of B for all X. And remember we have a logical equivalence of that. We prove biconditionals by breaking it into two implications, basically to prove the biconditional both ways. But these two statements here under the for every X are the definitions of subsets. So it's equivalent to showing that A is a subset of B and B is a subset of A. So the way you prove A and B are equal is by showing that A is a subset of B and B is a subset of A. All right, proper subsets are an enhancement of the subset concept where if you have A as a subset of B but they're not equal, then we can say that A is a proper subset of B. And we use the notation that open sideways U to indicate proper subset that has no line in it. So if A is a proper subset of B, then A is a subset of B, and there's an element of B that is not in A. Here we have a Venn diagram. Here's our universal set. Here's our set B and a set A. And this indicates that there's something in this area that is in B, but not in A. So A here would be a proper subset of B. All right, set cardinality. Cardinality is a counting of the number of different elements in a set. So first of all, we want to talk about two different types of sets. If we have indistinct elements, then we say that S is finite. Otherwise, it is infinite. So an example of an infinite cardinality set would be the set of integers or the set of real numbers. Cardinality then is defined on a finite set as just counting the number of distinct elements. Here's the cardinality of the empty set, and it has 0 elements in it. Cardinality of the English alphabet is 26. The cardinality of this set is 3, since it has 3 elements in it. And here's that set containing the empty set, and it has cardinality of 1. We don't get into a discussion of cardinalities of infinite sets in this class, but there are some nuances with that. Suffice to say that the cardinality of integers is countable infinity, and cardinality of reals is uncountable infinity. Yeah, a set of integers is infinite. All right, power sets. If we want to talk about all the subsets of a set, and we put them together in a set itself, it's called the power set of A. Here, all the elements of the power set are themselves sets. If A is the set containing lowercase a and b, then the power set of A is all possible subsets. Well, all possible subsets include the set itself and the empty set, as discussed earlier, and then all proper subsets as well. And it turns out that the size of the power set is 2 to the n. So the power set of A, B, C will have 2 to the third elements. And I will leave it to the listener to figure out what the power set looks like.